Hey team, welcome to the video that's going to be going over setting up RoadRunner from scratch on a test robot. Uh, this video is basically going to start with downloading the project. We're going to make a new project in Android Studio, do a quick overview of the test robot we'll be using, which I've got on the field right here. That test robot, we're going to go through the whole calibration process, setting up basically a mechanism drive here with 3 different dead wheels, as well as an IMU on the control hub. We're going to go through the tuning process. We're going to look at a couple different files we're going to have to change in RoadRunner. We're going to talk about mechanism drive class because we do have mechanism wheels on the robot, as well as the 3 dead wheel localizer class because we have 3 dead wheels on our test robot here. We're going to go through a little bit of FTC dashboard, which I'll show you real quick right here. FTC dashboard is basically a way to use the driver station from your computer as well as visualize some graphs and change some values. We're going to calibrate our encoders, find some constants that we can put in to allow our robot to drive around on the field autonomously, and then do a little bit of manual tuning before doing a final test run. This whole process is probably going to take about an hour. I'm hoping it goes a little bit faster, but this might be a pretty long video. But if you follow along, you should be able to take your own robot and set it up to use RoadRunner from scratch. We are using RoadRunner version 1.0. There's different versions of RoadRunner. I believe the previous one was 0.5 something. This year we're switching to 1.0 because the setup for it is just significantly easier. All right, so first things first, you got to download RoadRunner. RoadRunner is nice enough that it includes the FTC robot controller repository in it, and they tend to keep it up to date. You can see last week they actually pulled the latest robot controller code, which is nice. So all you got to do is go to github.com, right up here, Acme Robotics RoadRunner Quick Start. You can also just search for RoadRunner, you can probably find this, and get this onto your computer. The easiest way to do that, if you're not sure how to use Git, is to click the code button and then hit download zip. Once you do that, it's going to show up in your downloads folder right here. RoadRunner Quick Start Master. I've done this a couple times before, so I got that parentheses 1. And then you're going to right click and extract that somewhere nice onto your computer. I happen to choose Documents folder for this year's game Into the Deep, and I'm in a RoadRunner tutorial folder here, but you can put it wherever you want on your computer. Once you've got that, we're going to open it up in Android Studio. So I'm assuming you've got Android Studio already installed. Android Studio is going to be over here. I'm going to close out of this current project and we'll reopen it just so you can see what it looks like there. So when you open up Android Studio, you might have to do open here and then select the file that you just downloaded, or the folder, excuse me. So the folder was called 2024 RoadRunner Tutorial. It might not have this little Android icon on it yet until you open it up in Android Studio, but go ahead and just open that folder and it'll open up the project for you. This might take a little time to build. It took about 5 or 10 minutes on my Wi-Fi, so go ahead and give it time to do that if it needs to. Once it's done, you should see a little Android dude up in the top, and on the bottom you won't see any more progress bars going. It does take a while to download all the dependencies, but it should just do it on its own once you import that project. Also, if you want to use Git, which I would recommend, you can hit the Git button at the top after everything's done building. And I believe there's a button for create new Git project or something like that. You can make a Git project and do your first commit as well. Let's see if I can show you my first Git commit here. Yeah, it just says initial commit in it and talks about copying from that project. This is really nice because as we make changes to the files, once you do your commit and select everything, it'll all turn white, which means they're unchanged. And as we make changes to those files, it's going to show up in the Explorer view on the left side here. All right, so let me go a little bit over what the test robot looks like as well. So our test robot we've got set up on the field here, we lovingly call Bob. So I'm going to unplug it from our laptop here. Bob is pretty close to a Go Build a Strafer chassis. It's got the 4 mechanism wheels. This is a smaller version that we had from years past for a game where there was a little more limited field space, so you will see that the back motors here are actually sitting on top, but it doesn't matter what your robot looks like. We do also have dead wheels. These are the Go Build a dead wheels on the back. So we've got 2 parallel wheels on the side and then 1 lateral wheel on the back. So as our robot's driving forwards, we'll see the two wheels that are lateral to the robot, or excuse me, forwards on the robot spin this way, and then as we strafe the one sideways, we'll catch the strafing as well. Otherwise, it's a pretty standard robot. We don't even use the expansion hub. It is plugged in, but we don't use it for anything. All we have plugged in right now are the 4 drive motors and then the 3 encoders plugged in. Also note, we do not have encoders on our 4 drive motors. So the 2 motors underneath here and the 2 on top do not have their encoders plugged in. We only have encoders plugged in on the dead wheels there. All right, let me get back to my computer here. Okay, let's see. Oops. Let me make sure my screen capture is working. There it is. All right, so now that we've got RoadRunner downloaded and running, and we've got a robot we're ready to play with, all we're going to do is go through the quick setup guide. So from here, you can go down to the README and click on check out the docs. I've got the docs page up right here. So basically what we've done is gone through the quick start installation already. We've downloaded it from the page, and we're ready to go. There's this whole process for installing an existing project. I wouldn't recommend this. Just copy your files into this new project if you've got some already to run, like your teleops. Otherwise, we're going to go to the tuning page, which is basically how to set it up. I'm going to be reading through this with you. I have done this once before, but we're going to go through it together as well, just so you kind of know how we're going through and doing this. I did miss a few things the first time. I even read this page very carefully. Most details are only mentioned once and you don't want to miss them. As we go through, I still might miss details, but hopefully we'll get through them together. Great. If you're stuck and need help, go ahead and join the Discord here. People who have gone through that will help you as well. If you have really difficult issues, like you think there's a software bug, you can open an issue in the GitHub tracker as well. But more likely than not, you just need to reread the configuration here to get it all set up correctly. So like I mentioned at the start of the video, we're going to start by just setting up a few of the classes to be configured to work with our robot. RoadRunner does work with all different types of hardware configurations, so not just 4 mechanism wheels and 3 dead wheels, but we are going to do the config as if it is that. So our goal here for the drive class setup is get basic hardware configured. So we're going to be dealing with mechanism drive as our first file, and then the 3 dead wheel localizer as our second file to mess with. So let's open up mechanism drive first. It should be under team code, Java, all of these things here, and then mechanism drive. And this has a bunch of to-dos for us to work in. You will see the to-dos are in yellow here. So anything that has yellow, we're going to be doing the to-dos and then changing them. So we're just going to go in the order that it asks us here. So make sure the wheel motors are named left front, left back, right front, and IMU is named IMU. So if we scroll down a bit for the, I believe the constructor for mechanism drive down here. So this constructor is what takes in the hardware map, and then it's going to get all of our motor names here. So this is the configuration on the driver station. I'll show you our driver station configuration real quick. Get this over here. Oops, skip camera. All right, so this is our configuration for the driver station. Make sure you can see that. If you're not familiar with that, it's triple dots and then configure robot. Setups config file, we have control hub plugged in. It's a little bit bright. Let me see if I can get that done there. Control hub, motors, and then we have the names of all of our motors. You can kind of see it. It's a little washed out on the screen there, but hopefully you've done this before and you can make sense of what's going on here. We do have our motors named left front drive, left back drive, right back drive, and right front drive with underscores, which is a little different than they have named in their file. So we have 2 options. We can either change the configuration on the phone, or we can change the configuration in Android Studio. I prefer to just change it in Android Studio. So left front here for us is going to turn into left front drive. Left back turn into left back drive. Right back drive. And right front drive. So that's not required to change that. You could just change it on your phone, but we've got some other modes we're going to talk over want to change these here. We might also need to reverse motor directions. I'm getting ahead of myself here. So name your things. You should have an IMU named IMU. If you're using a newer control hub, not just an expansion hub with a phone, but if you have a control hub on the robot, there's already an IMU named IMU, so you don't have to do anything special for that. We do have to set the logo and USB direction of your IMU using the instructions. So I believe that's at the top. IMU orientation right here, so fill in these values. This one's pretty straightforward. You probably don't need the link for it. So this basically uses the logo of the robot here. So our control hub right here, depending on which way that's facing, depends on which axes we care about for the IMU. So the robot needs to know which way that control hub is mounted. In case it's mounted sideways, you would use a different axis of that control hub. So we have the logo facing up, and we plug in our USB on the left side here. So we're going to configure that in the code as well. So logo direction is facing up, and then USB is facing to the left there. So that's an easy change. We're also going to change the drive class variable to the drive class we're using. So in tuning op modes, there's a drive class up here, which is already mechanism drive, so we don't have to do anything there. That's convenient. And then we're going to say how our robot should track its position. There's a few different built-in localizers depending on how you're localizing your robot. This is basically what sensors does your robot have to know where it's going. Drive encoders means you have just encoders on the drive wheels. 2 dead wheels plus the IMU will work. We happen to have 3 dead wheels. We tend to like that setup a little bit better, so we're going to go with that localizer. So we're just going to copy this code here. And that code goes back in our mechanism drive, I believe, in our constructor. Let's see if I got it right. Yeah, right here. So drive localizer instead of that, a new dead wheel localizer. We're going to pass the hardware map and give it inches per tick here. Great. So really we're just going in order here, setting up everything as the docs are saying. So this isn't anything different than what the docs are doing. I just feel like it might be easy to go through it with someone else here. So there is a little bit here that if you want to change names of the localizer or correct motor names, we do have to do that as wheel. So we're going to go into our 3 dead wheel localizer, and you can see we have the same thing here where they're trying to get the names of our encoders. So this one's a bit tricky. We basically have to see which motor ports our encoders are plugged into and configure them correctly. So I'm going to show you the robot screen again real quick, and we'll trace some wires here. So we've got this Velcro cable management on our wires. Let's just take that off so we can see where everything's plugged into. The docs do recommend as well that if you're plugging in encoders, the left and right side, your parallel encoders, to plug them into ports 0 and 3 on your control hub. For hardware reasons, those ports read faster than the other ports, than ports 1 and 2 on the control hub. So we do our more important encoders on those 2 ports, and we get a little bit better resolution. I'm not sure if it actually matters. I'm sure it's true, but I don't know how much it'll actually affect our driving here. So we're just going to follow some of our cords here. So here's our encoder cable coming from our left dead wheel, and that's plugged into port, let's see, 0, which makes sense. And then our right one, tracing that wire, that's plugged into port 3. So let's just do those 2 first. So the left one is on port 0. We happen to know our port 0 is where our left front drive motor is plugged in. So that's going to be left front, oops, let me switch to this here. Left front drive. And then our other parallel encoder is in port 3, which using the config on our driver station here is going to be right front drive. And then our perpendicular encoder, the one on the back, we're going to have to trace that wire as well. So if we look at this guy, this is plugged into port, let's see, 0, 1. So port 1 is plugged into the left back drive. So we're going to do left back drive here. And as we completed that to-do item, we're going to get rid of all this yellow text. Android Studio has a nice feature where if you have this / to-do at the beginning, it turns your comment into a to-do, which just turns it yellow and you can search for them specifically. Great, so that sets up our localizer to tell it which ports each of the encoders are plugged into. So that's this bit here, and then again, port 0 and 3 should be used for the parallel dead wheels. All right, so now we actually get to run the robot. So it says check that the wheels are running in the correct direction. So they have a nice way of setting this up for us. There's a mechanism direction debugger we can use to make sure all the directions are correct. So this will just spin the motors and we're going to see which way they're spinning. There's also a dead wheel direction debugger where we can spin the wheels manually by hand and see which direction they're spinning as well. So we're going to move to the field and set those up as well. I'll show you real quick in code where we're doing that. So that's in our dead wheel localizer. We might need to reverse directions of some of our dead wheels. And for mechanism drive, we might need to reverse some of the directions of our motors. So let's take a look at the field again. And I'll actually bring the driver station down here and get on camera and show you guys how we're going to be testing this out as well. Just make sure you can see that. Yeah. So we've connected to our robot here. We're going to be using the teleop modes. There's a bunch in here as you're scrolling around. So we have a dead wheel direction debugger. We're going to be collecting mechanism motor direction debugger. Hit initialize and play. And then some instructions actually pop up on the screen here. Oops, actually got an error saying left front doesn't show up on the robot, which makes sense because we've changed some code and I haven't pushed it to the robot yet. So hopefully you know how to do that by now. We're just going to plug it in here into the control hub. In Android Studio, we're going to hit the stop and replay app button. It takes about 15 seconds here for our build to go through. Launching the bottom right of the screen here, launching on devices. We should see a little pop up in a second that says build complete. There we go, install finish. All right, let's try this again. All right, we'll unplug our robot, wait for our driver station to restart, hitting the arrow for teleop, and I'm going down to mechanism motor direction debugger. We'll hit initialize, no errors this time, we'll hit play. It'll give you some instructions on the screen to basically run motors individually. So the trick here is if you kind of hold your gamepad 45 degrees to the right, you have your front, left, and right motors and your back, left, and right motors. And when you push the button, it just spins the motor a little bit. So if we do our front right motor with the Y button, hit start A first, there we go. So the Y button will spin the front right motor, and we can see that it's spinning forwards, trying to pull the robot that way. Back right also spinning forwards. Our front left one actually seems to be spinning backwards. So our front left wheel needs to be reversed, and our back right wheel also spins backwards. So both left side wheels need to be reversed here. While we're on the field, we can also do our dead wheel direction debugger. So I'll show that as well. We selected that from the teleop mode on the driver station, dead wheel direction debugger. We'll hit play, and you'll see some numbers for the dead wheels here. So our parallel dead wheels both show like -1,000 because, you know, we spun the wheels a bit with the other op mode maybe. And we're just going to push the robot forward kind of virtually. So if the field's coming under the robot, our left dead wheel is going to spin this way. And that is now increasing. We're at -3,000, -4, actually decreasing, -5,000, -6,000. So our left dead wheel needs to be reversed. And then our right dead wheel as well, if we spin that, has the same problem. So both these dead wheels, as we push the robot forward, you can do that as well, are increasing negatively, so I guess decreasing. So we have to flip those. And then our back dead wheel here, your perpendicular dead wheel, should increase as you move leftward. It says on the driver station right there. So we'll move the robot to the left, and that one actually does increase. We went from 0 to about 1,000 in that. So it looks like we need to reverse both our left drive wheels and our two parallel dead wheels. So we'll head back to the computer here. And reverse some directions of things. So this is our mechanism drive here. This was both of our left wheels need to be reversed. So that was our left front and our left back. Set direction, reverse. And then in our dead wheel localizer, it was both of our parallel dead wheels that need to be reversed. So parallel 0, reverse. And then parallel 1, direction, reverse. And we'll get rid of that T because we have now to done it. Great. So we still have to push that to the robot, but let's go ahead and see what's next in the docs here. FTC dashboard. All right, that's a pretty cool tool. Let's talk about that one next, actually. So as we're tuning and configuring our robot, there's going to be a few cases in the near future where we're going to want to tweak some values very slightly. You could change your code and then push it and see how it behaves better or worse, and then push code again and see how it behaves, but it's really not that fast of a process. We also get some really nice graphs that are going to help us with our tuning of the robot as well. So we can actually get real-time graphing and real-time variable changing through a tool called FTC dashboard. So this actually comes pre-installed with RoadRunner. So just by copying this RoadRunner project, you'll already have FTC dashboard ready to go. All it requires you to do is actually change your Wi-Fi network to connect to the robot controller. So we'll do that down here instead of connecting to our Wi-Fi here. We'll let this refresh, and we should see our robot controller pop up. So this is the same Wi-Fi network that your driver station actually connects to. So this is the Wi-Fi network being put off by the robot itself. Now it should connect just fine. You might have to type in your password. It would be the same password that you set up when you put your driver station to connect to the robot controller. But you won't have internet access while you're doing this, because instead of going to your router or whatever gives you internet, you're now going through the robot controller, which does not have internet. But that's okay, because it hosts its own local website that you can access. So go ahead and copy this web address into your web browser, which should take you to the FTC dashboard. I'm going to reload this, make sure it seems to work. There we go. So you can play around with the view here. I think the default view might not show that much, or it shows the camera here or something. We're going to be using the field view a little bit later, so I prefer that. On the top left here, you do have the op mode, and you can actually pretend that this is a driver station and do driver station stuff. We also have configuration. We're going to be changing some numbers in here later, and we'll be using some graphs as well to see how the robot behaves. So that's FTC dashboard. It's just kind of nice to have set up. This doesn't work for you yet. Take the time to figure out to get it to work. It should just be as easy as connecting to the Wi-Fi network and typing in that URL to get to the dashboard. All right, so now that we've got everything hardware configured, we're going to be doing some push tests. So I'm going to talk a little bit as I push code to the robot here. Give me just a second. I can show you guys what I'm doing. So let me plug the robot in. So the way RoadRunner works is basically with a control system called feed forward. So a feed forward control system basically means you're going through a series of steps to see how the robot behaves when you give it certain voltages, different powers. So what we're going to end up doing is saying we're going to give it 1% power, 5% power, 10% power, and see how fast the robot is moving. Then in the future, if we want the robot to go somewhere and autonomous, we kind of already have that mapping. We know, well, if we need to drive this far, we can give it this much power for a fixed amount of time and know that we're going to get there. So feed forward is basically a forward prediction of we know how the robot behaves, and we're going to tell it to get some power to the motors and expect it to behave the same way in the future. To do that, we need to figure out some inherent facts about the design of our robot. And some of those facts are going to be things like when you move the robot, how far do the motors move? Or when you give 17% power to the robot, how fast is it driving at that time? So this whole process that we're going to do is called the tuning process. Everything we've done so far is kind of just the mechanical setup of the robot. As long as you're not, swapping out your chassis or whatever, those things aren't going to change. Everything from here on is basically going to change as you change the design of your robot. So let's keep going through our tests here, our setup here. So first we're going to be doing this forward push test. This test is basically a way to empirically figure out, which is just means through testing, through physical testing in the world, how far the robot moves compared to how many ticks the encoders read. So think of it like figuring out the size of your dead wheels, right? So your dead wheels might read 1,000 ticks every time you move 1 inch or something like that. Then in the future, if you realize that you've moved 5,000 ticks, oh, I must have gone 5 inches. So to do this push test, we're just going to follow the instructions as they say here, placed on the tiles with plenty of room in front, square it up with the grid, and make note of its starting position, run forward push test and push the robot, and record the ticks traveled from telemetry. So with that, we're going to do some math and figure out inches per tick. Real important here, make sure the wheels don't slip. So the motor should spin freely, and we're just going to slowly push it across the field. So let's go to the robot here and do our forward push test. So we pushed our code, which is important here because remember we've set the encoder directions. So if we push it forward and it thinks it's going backwards, that would be bad. So we've got our encoder directions set now. So we're going to do the forward push test. We're going to hit on our driver station, teleop, forward push test. We're going to get our robot in a nice starting position. So I'm lining it up with the corner of the tiles here. So looking top down at the robot, I've kind of got the left edge of this piece of channel on the tiles, and then I'll line the front edges up with the piece of the tiles there. We'll hit initialize, play. And so far it says ticks traveled 0 on the driver station. So now we're just going to very slowly and very carefully push the robot across the field to a fixed endpoint. So I'm using the front of the robot as my reference point, and the front of the robot is right at the start of this tile. And very slowly and carefully, I'm going to try and push it as parallel as I can, trying to keep basically this left side here lined up with the left side of the field, making sure that the dead wheels stay in contact the entire time. For this test, speed does not matter, so go as slow as you need to be consistent. And I'm going to go all the way until, you move my safety barrier, the front of the chassis is kind of lined up right with where I can easily measure with a tape measure. So that looks about right to me, right at the front. We're going to take a note of how many ticks it's moved. So 39,832. 39,832. Now, of course, this value is going to be different for you. Let's just open up Notepad real quick so we can write some stuff down. That was 39,832. Let me make sure of that real quick. 39,832. Yep. So that's how many ticks we traveled based on how far the robot moved. So now that we know ticks, we need to figure out inches. So that's pretty straightforward. We have a tool to figure that out. We're going to get a tape measure and measure where the robot ended in a straight line all the way back to where the robot started. So for me, that's 117 3/4 of an inch. So I'm just looking kind of at the tape measure at where it started on the field here. It's 117 3/4. All right, and then to figure out ticks per inch, we just have to do a little bit of math. So ticks per inch would be ticks divided by inches. Ticks, I'm pulling out my phone now, 39,832 divided by 117.75. I do that right? Ah, I did that wrong. Inches per tick. I was going to say I should get a fraction here, and I got a big number. So inches per tick would be 117.75 divided by 39,832. There we go. And that gives us a very small number. And we're going to put that, let's see, inches per tick in your drive class. So if we go to our mechanism drive, I believe at the very top, there's an inches per tick, and we're going to type our magic number in there, 0.002956165896. Probably way too many points to matter, but it's kind of fun to type them all in, I guess. Cool. So that tells us that if we move one tick, we have moved, what is that, 2/1000ths of an inch. So we'd have to move, I don't know, what is that, like 500 ticks to move an inch, which, I don't know, maybe that sounds right. All right, so that was our forward push test, and that basically tells the robot, again, calibrating how far it moves with how much our encoders move. So now if we can do the backwards math, right? We can say if we want to move 5 inches, we're expecting that our ticks should move by some specific amount. Great, so we're going to do the same thing again with the lateral push test. This is the same thing, but we're going to be strafing. So set the robot as it was before, slowly push it to the left, and set lateral inches per tick to distance divided by ticks. So that was inches per tick, then we're going to do lateral inches per tick. So I'll go back to the field view here, and we'll do the same thing. I'll stop my op mode for the first test we did, and we'll just do the second test real quick. So I'm going to set it up on the field just like this. Kind of get the back of our chassis now lined up with this side, and then the side of our chassis lined up with where our tape measure is. I think I'm going to keep the 117 3/4 starting point here. Open up teleop mode here on the driver station, go to lateral push test. Ah, I seem to have made the same mistake as before. Let's go back to the docs. Yep, so lateral push test here, and I think this got me last time I did this earlier, is mechanism with drive encoders only. And it's nice because I tried to run lateral push test and it actually threw an exception saying you don't need to do this. So that's pretty nice. So again, we're not using drive encoders on our robot. We do have mechanism wheels, but we are doing the dead wheels. So we're just going to move on to forward ramp water, which is for dead wheels only. All right. Let's set the robot up there. All right, so forward ramp logger is going to be kind of the same idea as our forward push test. Instead of figuring out now how far the robot moves and figuring out how much our encoders change based on that movement, we're going to be doing something a little bit differently where we're going to slowly increase power and see velocity over time. So this is going to give us our static and velocity feed forward parameters. This is basically the reverse math here. So with feed forward, the way this works is we're going to figure out how the robot behaves when we give it specific power values. So we're going to increase the power very slightly each second, and we're going to see how fast the robot is moving. And now that we have our forward push test inches per tick, it now knows, based on how many ticks it moves, how many inches per second it's traveling at. This one's actually pretty fun. We get to use graphs and stuff for that. So let's do the forward ramp logger here. Place it on the tiles as much distance in front as possible. Start the op mode and press when it reaches near the edge of the tile. I do have a little bit of a safety net set up here. It's a bag of dog food. But as the robot goes forward, if it doesn't stop in time, just make sure it has something safe to run into. A playing field wall is fine, but I'm working in a garage here, so I've got what I got. So let's go ahead and do the forward ramp logger. So I'm going to go to my op mode here. Ah, gets me every time. We do have to push code again because we changed that inches per tick value. That is, I believe, required for these values to come out correctly. So I plug the robot in, push code again. Wait a second here for the code to push. Goes. Now we'll be doing the forward ramp logger test. So we're going to wait for our robot driver station to restart here. Teleop, forward ramp logger, hit initialize, hopefully no exceptions, and then let it run. So you'll see the robot slowly start to increase power as it goes forward. Mine actually wasn't aimed very well, so I think I'm going to try that again. If your robot does start sideways, one trick that I found, sometimes if you have some of the wheels turned when you start, like some of the slop in the wheels is one way or the other, it might start off a little bit crooked. May have just been an aim issue, but I'm just going to go ahead and run that a second time. Make sure we get good straight drive out of it. And this robot just likes to turn left. All right. We'll try it one more time. I'm going to intentionally aim it a little bit to the right here. See if we can get a little more distance. The reason this is important here is the longer you let this run for, the more accurate this value is going to be. You'll see why in a second. All right. We'll take a look at that graph. I'm not sure if I stopped it before or after it hit that hard stop there, that bag of dog food, but we'll bust open the graph in the dashboard and see how it turned out anyways. All right, so this one's kind of fun. To figure this value out, we don't actually do the math ourselves. It's going to do it for us. So once you've run that test, you can navigate to this web page in your web browser. Just like that. And you should see this RoadRunner forward ramp regression. So we're driving forward, we're ramping up speed, and the regression is figuring out the resulting value of that. So you click the latest button right here. That actually looks like a pretty good test. And you'll see a bunch of data points that got collected. So this is pretty fun. There's two different values that we care about here. The first one is how much power do we need to give the robot until it starts to move, and this is measured in volts. So you can see from 0 volts all the way up to whatever the value is here, the robot just did not move. And that's pretty typical for these robots. You know, there's some friction, the motors don't want to spin, the robot has some weight, the wheels dig into the playing field floor. So there's some static amount of friction we need to overcome. So that value is actually computed for us, and that's this Ks at the top right here. So 0.7 volts required to get the robot to move at all. The next value we care about is basically the slope of this line. So we need to know, it's cool that it's linear, right? This isn't like a curve, this is just a straight line. So we can look at the increase of speed that we get based on the voltage that we're applying. So this is ticks per second, and you can see these are actually 1,000, 2,000, 4,000, 6,000, 8,000 ticks per second based on the voltage we give. And all of these dots are the samples that the robot recorded, and as we gave more voltage to the motors, we counted how many ticks per second we traveled, and that gives us this linear regression, which is pretty cool. There are tools here. If you find some outliers of data, some dots, way off in the distance, you can actually box select and remove those. They do talk about that in the docs right here. There you go, grade points measured here. You can select regions and remove points with E or exclude to add or remove values. I'm pretty happy with how this looks. Every time I've done this, I've gotten pretty good values, so hopefully yours looks pretty similar to this as well. So what we care about after running this test is to basically get these values and put them into our code. So kV, remember, is how many ticks we get per voltage. So let's see here, kV. Make sure I'm doing that right. copy the values above the plot into the KS and KV fields in the drive class right here. Yep, so KV is going to be that number here. And then KS is going to be this number here. And again, remember, all the robot did here in this file was basically say, how much voltage do I need to apply until I start moving? So it just slowly increased voltage until it moved. And then once it started moving, it said for each increase in voltage that I give it, how many ticks per second do I travel? And this is actually the inverse of that. So this would be the slope of the graph here, right? So voltage per ticks per second. So for each 0.0005 volts you give it, you get one more tick per second. Same idea. Cool. So hopefully that process makes sense. We're going to be doing this a few more times. So that gives us our KS and KV values. Now we're going to get lateral inches per tick. Let's see, mechanism with dead wheels only. This would be us. So the reason we didn't have to do, I believe, the manual for this earlier is because we have this lateral ramp logger for us. So if everything's configured correctly, the logger op mode will move the robot to the left, increasing speed, similar to forward ramp logger. Stop at any point, keep in mind longer runs will collect more data. And then we'll go to the same thing, but instead of, what was the period here, forward ramp, we're going to be going to lateral ramp, and we're going to put that into lateral inches per tick. So let's go ahead and do that on the field. So lateral ramp logger here. Now, I'm not sure if this one is going to require us to push the value that we just set for KV and KS. I believe it is. You know what? I'm not going to take a chance on that. I'm just going to push code right now anyways to save a little bit of time. I'll just plug the robot in. Our KV, KS and KV are set in. Build finished. We'll wait for our robot and driver station to restart. Run our teleoff lateral ramp logger. Hit initialize, hit play. We'll let it go as far as we can. Make sure we hit stop before it gets to the end. I'm just going to leave the robot there for now, because I want to see some data. All right, back to our computer here. So that was our lateral ramp logger. So we'll go to this URL instead, which is the same as before. Instead of forward ramp, it's lateral ramp. And we actually get to put in a few of our parameters here before it shows. So if you just click latest, you're not going to see anything. You do have to put in some parameters that already exist. So we're going to go back to our code and type in our inches per tick. Oops. We're going to put in our KS. That goes over here. And our KV. And you'll see once you type those in and click update, you get a similar looking graph here. So same idea. There's a little bit of dead time here before the wheels move, but we kind of already knew that from our previous test. Really what we're getting here is just our expected velocity from the feed forward in ticks per second, because we know how the motors behave based on the power we give them, and comparing that with our actual velocity. So we're going to take our value here and get lateral inches per tick. So we're kind of doing the inverse math of before. We know how the robot behaves now, and now that we have those parameters, our KV and our KS and our inches per tick, we can kind of figure out our lateral inches per tick, which actually looks pretty close to our inches per tick. This is 0.29, sorry, 0.0029, this is 0.0023, which maybe makes sense because robots don't like to strafe quite as much as they like to drive forward. So lateral inches per tick here, we're just going to paste in our new value. All right, on to the next step. All right, next is the angular ramp logger. This routine is similar to the last, except it rotates in place instead of moving forward. You can change the power ramping parameters inside power, run the routine using the same instructions. If you're doing drive encoders, which we're not, you can follow this. Because we have dead wheels, the angular ramp logger is going to do this. I will say that this is a very important bullet point. We're going to be setting multiple values here for our track width ticks value. So don't forget when we get there, we're going to be copying multiple values in. So let's go back to the field and run our angular ramp logger. Once again, I think we're going to push some code as well. Make sure that the value that we get, that we just punched in, is going to be recorded while we're running this op mode. So I'm just going to go back to the computer here, plug it in real quick, wait our 15 seconds. I'll be honest, I'm not positive which of these values is used in which of these op modes. I'm assuming that the lateral inches per tick is going to be used when our robot is spinning in a circle, because we do use that lateral encoder, that dead wheel on the back of the robot. But I'm not positive, so I'm just going to push it and be safer than sorry. All right. Now we're going to run our angular ramp logger. This is just going to spin the robot in a circle. I'll pull it out where we can see it a bit better now. Wait for everything to reset. Angular ramp logger. Hit initialize. Hit play. And watch it slowly increase power until we start to turn. At some point, the robot's going to reach max speed here. That sounds about right. So I'll hit stop. And we can go look at our graphs. So because we're using dead wheels, we're going to go to this location in our web browser. I'll just replace this guy with this. Dead wheel angular ramp. This is going to want our parameters, our feed forward, velocity, and static. So we'll copy our static. Remember, this is how much voltage we need until the robot actually moves. And then this is the how many ticks per second we move, our speed per velocity we give the motor, per volt increase. We'll hit latest, we'll hit update, and get some values. I gotta say, these are some pretty nice looking graphs too. I always love seeing linear regression graphs when you're plotting data over time or comparing two different things. So in this case, ticks per second against radians per second, and you always get a really nice linear setup here. If you have a bunch of outliers and stuff, a bunch of gray dots everywhere, it doesn't come out quite as nice. But this is cool. Also note, when we're doing this angular ramp regression, I said it earlier, there's a bunch of values that we're going to be copying. Make sure you scroll down and see all of those. So we're going to start copying those values over. We have track width here. So this was basically, let's see, track width ticks. How far apart the two parallel dead wheels are, the left and right side dead wheels in number of ticks. And we call it our track width. Think like if you're driving forward, you have your left and right track, and how far apart are those? We also have some other values. We have the Y position of our wheels. So this is a parallel wheel track width regression value up here. Parallel wheel zero regression is right here. So that gives us a Y position. I believe this goes in our other file, our 3 dead wheel localizer. Yep, Y position of the first parallel encoder. So we're going to punch that in. Parallel wheel 1 regression. We have this guy here. You know, just for fun, I can show you guys. It looks like when we were spinning, we did hit a max value, got a bunch of data points here. If you do want to exclude data points, you can just put a little box over that and hit the exclude button here, and that grays it out and gives you a new number. Now we're at 2373. I don't think it's actually going to change anything. 2352. It's a pretty negligible change. Let's see, that was our parallel regression. But you can play with that as well and see if you want to tweak any of those numbers based on what you include and exclude from these values here. And then perpendicular wheel position as well. We're just going to go down here. All right, and we're almost done tuning here. So let's push this code, and then we're going to start doing some manual tuning. Oh, I'll switch back to the robot on the field here. Oh, I was showing the robot the whole time. Well, let me show you real quick. What I was doing there, I was in the 3 dead wheel localizer. On the screen here, we went to the dead wheel angular ramp. You might have to just use your imagination here. Sorry about that. We typed in our feed forward parameters for KV and KS. We copied those from our file from earlier. We do have the track width here for our track width regression. So we copied that into our dead wheel localizer code under, or no, excuse me, width was in our mechanism drive code right here. 4121 got copied from here. And then scroll down on this page, this dead wheel angular ramp regression. Scrolling down, we see our parallel wheel 0, Y position. That gets copied into our dead wheel localizer. Parallel Y position here, 2337, negative. If you're not happy with some data, I showed a box select here, so you can box select and exclude it. So it thinks our Y position is 2352 for this other wheel, and if we exclude that, it goes to 2373. So if you don't like some of the data points you see here, if you have outliers or big clusters, you can change that. I'm okay with whatever this is. So 2352, we put right here. And then our last one here is perpendicular regression, X positions. This is how many ticks it is back on the robot, 2322. And I copied that into here as well. Sorry about that. I didn't have the right screen showing there when I was talking a little bit. All right. So now back to our tuning. We're now at the manual tuning, which is pretty cool. So everything we've done up to this point, the computer can basically figure out on its own, right? We had to copy paste some numbers around, but once you kind of tell it, here's how the wheels are set up, forward is this direction, push the robot this distance and tell it how far it actually traveled, then these op modes with a little bit of your work can basically figure out, increase velocity, how fast am I moving? And then, in the future, if you give it that velocity, it'll move that fast. Or turn or strafe or whatever it needs to. So what we're going to be doing now is actually a little bit of interactive tuning. So this is where it gets a little bit, I don't want to say opiniony, but you get a little bit more influence over how the robot behaves. Right now, the robot can do some stuff. It will try and drive around and we'll roughly know where it is based on all of that. But really the problem now is it doesn't know how to correct itself. So when something does go wrong. So for example, if we're trying to reach a certain velocity, we might always lag behind because we might not give it enough voltage to get there, right? So if we're trying to go at 5,000 ticks a second, we might know that that's 4 volts on the motors or however the math works out. We give it 4 volts, but the robot starts to accelerate and it doesn't get there soon enough. So now we're going to do some manual tuning and basically make sure that we accelerate at a reasonable rate. So that's what this manual feed-forward tuner is. And this one actually uses a lot of features in FTC dashboard as well. So this time around, we're going to be actually running our code through FTC dashboard. If you're not sure how that works, you just go back to FTC dashboard, which I think we had set up from earlier. I'm actually going to take my driver station off the field and get a little bit more space set up on the field here. I'll show you what I've got going on now. Our robot's going to be doing a little bit of driving on its own. So we're going to give it a nice, safe spot to drive around in. I'll get this tape measure out of the way as well. And now we're going to be running our op modes through FTC dashboard. All right, so we're following the manual feed-forward tuner now. This drives forwards and backwards distance units. I think it's about 5 feet by default to give you different feed-forward parameters, or to finalize the feed-forward parameters. So we're going to open FTC dashboard, which is what we've got open here, run the op mode, and graph vref against v0. We're going to change Ka, which is basically how fast we're going to accelerate, and slowly increase it until we start to get our plots to match. Now at this point, remember the robot has no feedback and may drift over many cycles. So our robot's going to drift a little bit to the left because we saw it run earlier. It likes to drift left. So we can press Y on the gamepad to pause it, and then I'll walk down and reset the robot, and then hit B to get it to continue driving. So let's see what that looks like. So we're going to run the manual feed forward tuner. Hit initialize. This is the same as running it on your phone. Hit our graph. Oh, I think we have to start it and then hit our graph. So I'll show you a little bit first of the robot on the field. I'm going to hit start here, and you'll see the robot's just going to drive forward, and drive backwards, and drive forwards, and drive backwards. And while it's doing that on our computer, we can hit this graph button up here and do V0 against Z-ref. And hit the graph button. And you'll see we got two lines coming up. Now my robot's kind of gone rogue on the field here. I'm going to be switching back and forth a lot, so let me get that set back up. When you do hit the Y button on the controller to stop it, it's going to want to go forwards again, so always try and reset it kind of back to the middle. So this time I'm going to be showing you the graph on the screen. I'm showing the screen now again, and I'm just going to hit B on the controller to get the robot to drive forwards. And you'll see that red graph on the screen is showing what our expected velocity is, and the blue is our actual measured velocity. So kind of as expected, we're lagging behind. Even though we're giving it a velocity to try and get there, the robot has some mass and it's not accelerating perfectly. So I'm going to stop the robot again. It seems to have gone off the field. Hopefully you have a bigger field set up than I do. So we're going to start tuning some variables. We're going to be setting Ka to a really small value and kind of see how that changes. So these are all of our, when you see configuration on the side here, these are all of the classes that have configurable variables inside of your Java files here. So when you see these things that say params, these are basically all the things you get to change. So Ka is in the params of our mechanism drive class here. So we do need to set this in code eventually when we push to the robot, but while the op mode is still running, we can just go in and change this dynamically. So we're going to go into mechanism drive over here and go to params. And you can see all our values here. Some of them we've already set from our code, and we're going to change Ka to be some number. Make sure you hit the save button at the top here, and then we're going to hit the B button to continue the op mode, and we can see our graph. So didn't do much of a change. Let's get rid of the 0 and hit save and see how that behaves. What we're trying to do is get these blue and red lines that are kind of straight here at the top and bottom half to be working with each other. Now the robot just slipped off the field a little bit, so I'm going to pause the robot again, get it lined up on the field. As you see me do this a couple times, hopefully it'll kind of make sense. We're going to hit B to continue. And I'm going to cut a couple more zeros off the Ka value. I happen to know what it is because I've done this before. And you'll see after we make that change, now our red and blue lines are basically synced up with each other as it's trying to accelerate. Now this deceleration that happens here, that's where it flipped off the field. Don't worry about that. This deceleration bit where it kind of overshoots, we're not too worried about that right now. Really what we're going to be thinking about is this overlap right here. Okay, so my robot just spun out on the field there because it fell off. That's that weird gap there. But I think I'm happy with this Ka value. Go ahead and keep playing with it. Your robot's going to be different than this one. So we'll copy that Ka value over into our code here, and we'll just say that's what we should be running with. Cool. So that was the feed forward tuner. I'm going to push code because I believe that's important at this step. And after that, we're going to be doing the feedback tuner. So feed forward, again, is basically we're seeing how the robot responds when we give it a certain value. And we're measuring that response. So in the past, our feed forward tuners, we would give it some velocity and see how fast it would move based on that velocity. And then in the future, when we want to go that velocity, we can do it. So basically did that with acceleration. We gave an acceleration profile that said get up to this speed at this time, and we graphed it. And we can change that Ka so that it knows basically how much more power it needs to meet some kind of acceleration profile. All right, I pushed some code, and now we've got the last tuner here. This is the manual feedback tuner. Let me see how long. This video's already gone an hour, so I promise this is the last one. We're about 5 or 10 minutes away from being done here. We just pushed code. Let's get doing the manual feedback tuner. So this is where everything kind of comes together. So as I've been explaining feed forward is this whole concept of, again, you measure how it behaves in real life, and you expect it to behave the same on the field. That doesn't always work because things get in the way. Batteries change, robots get knocked off course, a sample might get in your, one of the elements in this year's game, whatever it might be called, might get in your way. So the last thing we're going to be doing here is a feedback tuner. So this is really when we get to change how the robot behaves when it doesn't follow where it's supposed to be. So feed forward basically says, in a perfect world, we can control this robot. The feedback basically looks at how the robot is currently positioned on the field, where it should be on the field, and then gives it a little bit of extra power on those wheels to try and get to where it should be. This is kind of like your error correction. So the way we do that is we run the manual feedback tuner, and there's a couple different parameters, just 3 of them that we need to change to get this to work. So it'll explain here for mechanism drive, there's 2 gains for each direction. So there's a forward, how if we're too far behind or ahead of our target, how much power do we adjust? That's our forward. Our lateral, let me just check this real quick. Yep, our lateral is going to be if we're too far left or right, how much power do we want to strafe to get back? And our heading, if we're facing the wrong direction, how much more power do we give the left or right side to correct that? So each of these has a position gain and a velocity gain. Position gain is going to be basically like a proportional term for position PID. So the farther off you are, the more power you're going to get. And velocity gain is basically going to dampen that effect, if it, like a derivative term of a PID. So we're going to do one parameter at a time. Start by setting a small value like 1, nudge the robot and watch it get corrected. And we're just going to skip velocity gains because you probably don't need it if you're watching this video. So we're going to run the manual feedback tuner. So on our dashboard, we'll go manual feedback tuner. The robot is set up again on the field, ready to drive forward. It's going to be doing the same lines that it was doing before, forward and backward repeatedly. But this time it's going to tell us where it thinks it is on the field. If you haven't already, hit this drop down in FTC dashboard as well. Make sure you have field selected on the left side because I believe it'll show you where the robot is on the field as well. Great, so we've got manual feedback tuner set in our drop down here. Now we're using feedback from the encoders to correct ourselves. We do have some parameters again that we're going to be playing with. So we have forward, lateral, and heading. I believe the code is named a little bit differently. Yeah, they call it axial, lateral, and heading. Axial is just forward and backwards, lateral is left and right, and heading is your rotation. Sure, the turn kind of gives you a hint there for that one at least. It says start with values at 1. We're just going to run it without those values, and you can see what happens. So green is where it's supposed to be. Blue is where the robot actually is. And if you look at the robot on the field, it's pretty far wrong in terms of where it should be, but at least it knows that it's wrong, right? I'm going to stop the robot here because I'm kind of running off the edges again, but you can see it actually does a pretty good job of tracking where it is, even though it doesn't correct itself when it is wrong. So let's put a value in for those gains, and we can actually see how it corrects itself. So for our axial gain, we'll just put a 1 in. For our heading, we'll put 1, and our lateral, we'll put 1. It does say tune 1 at a time. If your robot is mostly straight, you don't have to put 1s in each of those. You can leave 2 of them at 0, maybe start with axial or start with heading gain. For me, the robot drives pretty crooked, and I have a small field here, so I'm putting 1 for all of them so that it does something useful. Make sure you hit save. We'll hit initialize and start. And you can see the robot driving around now. Well, there's a robot on the field. And you can even see only after setting those values to 1, we now have a little bit of correction going on. So green, again, is where we're supposed to be. Blue is where the robot actually is. Let me show this screen again. You can see our robot now not driving off the tracks. So green is where we're supposed to be. Blue is where we're actually is. And we're actually tracking pretty well. So we're going to change one thing at a time. The first thing I'm noticing is we're getting pretty far ahead of where we're supposed to be and pretty far behind when we get all the way back on the field. So that would be our axial gain. You can kind of think of this green or blue line as our axis, and we're going to change that axial gain to see how the robot behaves. So let's just go from 1 to 2 and hit save, and you can see how it responds in real time. So now we don't seem to be overshooting quite as much. We're a little more behaved. I don't know. Let's go up to 4 and see what happens. Now we're pretty snappy, right? So that blue line seems to be following the green line. And again, the robot is doing this in real life on the field. Now that we've got some gain values, some feedback to know where we are on the field, we're actually tracking it pretty well. So you can keep playing with these values. I'm going to show you what happens when you go too far as well. So let's just give it 20 for axial and see if I regret this. You can almost see it happen in the graph, but really if you look at the robot, you can see what happens. So when it gets to the end of its motion here, you'll kind of notice it jitters forward and backward right there. There's that little extra jitter. So if you give it too much gain, here I'll even go to 40. We can keep watching the robot here and see how it behaves with 40. There you go. That's a pretty bad gain. We'll go back to I don't know, 5 or so. So 40 it seemed to be real unhappy with. So what ends up happening is if you have too much gain, then if you're off by maybe half an inch or an inch, it might give the robot 100% power in the other direction. And the robot's going to behave erratically because that's too much power to correct itself. You want just enough power so that you get that correction. So go ahead and do this for your axial gain. Do it for your lateral gain as well. So the left and right. If I go back to the graph on the robot here, you can see that laterally it's actually tracking pretty well. We hovered a little bit to the left going forward there, a little bit there as well. So I don't think we need to change our lateral gain, and our heading seems to be fine as well. So I like these values, axial of 1, heading lateral of 1. So we're going to punch that in our code real quick as we kind of get to the end of this video. Axial 5, lateral 1, heading 1. Now, as your robot changes throughout the season, if you add more weight or if things shift around, or maybe just as you start writing some op modes, some autonomous modes, you realize that, it's kind of jittering a little bit or it's not quite catching up the right way. You can always go in and change these parameters in the future as well. I'll show you the robot driving forward and back on the field as well, which is nice. Now we've been running for a couple minutes here, and you'll also notice the robot is drifting a little bit. So on the field, it's forward there, and as we come back, we're a little bit offset to the right side. That's normal. These encoders aren't perfect. You are going to have loss over time. If you look back at FTC dashboard, the robot does think that it's centered. So this isn't a tuning issue at this point, the robot not being straight on the field, because as far as the robot knows, it's doing the right thing. What ends up happening is the robot just doesn't know that it's off. You can go back through the tuning if this is an issue for you. Maybe we could get a little more accurate with our lateral inches per tick value. That might give us a little better reference so that we don't get that rotation. But gyros drift over time as well too. So op modes autonomous is only 30 seconds. So as long as you're accurate enough for autonomous, you should be good. So anyways, I'm going to stop the robot. It seems to be getting to work out. Wait for it to get all the way back here. Make sure we punch those values into our code here, 5, 5, and 1. Didn't seem like we need velocity gains either. So go ahead and push that code. Once you're done with that, there is one more program you can upload, you can run. It's a spline test that just does validation. I will push code and show that real quick just because it's fun. It just makes the robot do a little arc on the field. So I'm going to push code here real quick and show you what that looks like as we finish up. All right, our build's done here. And I'll show you how I'm going to set this up on the field too. It's a little bit different because I'm on partial field here. So what this arc is going to end up doing is moving um, forward from the robot about 2 tiles forward into the left and face this direction, and actually come back and turn this way and kind of end up on the car. I don't quite have enough room to show the arc off, so it might drive off the tiles here, but you should have enough room on a half-size or full-size playing field. So I'm actually going to run it from FTC dashboard as well. I'll show you this blind test here, just so you can kind of see how it works. I'll show you on the dashboard first, and then I'll switch to the robot and run it a second time. But it is cool. As you end up programming your autonomouses as well, you can use this FTC dashboard to see which paths your robot is going to be taking on the bottom left side here. So if we hit start, you'll see it does that arc for that test, which is pretty cool. And then I'll reset the robot for you here. Hopefully your robot is doing something similar to this. If you are getting weird results at this point, you're just gonna have to go back through the tuning process and figure out what steps you need to rethink or redo. So I've got that robot set up there. I will say if something's wildly wrong at this point, it doesn't hurt to start over as well. This whole process only took us about an hour, and we've got a robot following a pretty steady arc there. It did, I think, clip off the side of the field, which is why it twitched a bit, but it seemed to recover well enough. So anyways, we've made our way through all of the tuning here. Hopefully you learned a little bit as we went. It was a bit of a follow along, but we did manage to go basically from scratch to a fully tuned RoadRunner ready robot in just over an hour. So surely if you pause the video and follow along, you've been spending more time than that, but this process should give you a pretty reasonable guide and a little bit of video to show you what that process looks like. Thanks for watching and good luck.